Okay, let's look at additional topics. That's not a very informative name. Additional topics for the SAT are geometry, trigonometry, complex numbers. We're going to start with geometry. And as I break down geometry, I'm going to think of it as two different types of questions broadly. Questions about angles. What's the missing angle? Solve for the angle. And questions about lengths. What's the missing length? Solve for the length. But wait a second. What about areas and volumes, you might ask? Areas are lengths squared. Volumes are lengths cubed. Hopefully we're going to learn to appreciate that because it actually has some significance for certain problems and correct units and like and unlike terms, etc. So with that, let's start with angle theorems. How do I solve for angles, missing angles? What theorems come into play? First, we're going to discuss the simplest case, vertical angles. If I have two straight lines that intersect, the angles opposite that intersection point, x degrees, they are congruent. Now that's just a fancy name for saying they have the same measures in every way, shape, and form. Okay? Well, likewise, those would be vertical angles as well, and those would be congruent. So if x equals 40 degrees here, x would have to equal 40 degrees over here. Okay, next, number 2. Angles along a line or linear pairs. So angles along a line. If I have a line and I have an angle A and B, and if I look at A and B together, they actually span the line, which is half of a full circle. So they actually span in degrees 180 degrees. So the sum of linear pairs or angles along a line is 180 degrees. In another word, we call that supplementary. Supplementary angles add to 180 degrees. They don't necessarily have to be linear pair postulates, but linear pairs are supplementary angles. They do add to 180 degrees. Or in the case of radians, pi radians. We'll talk about that later. Okay, number 3. Sum of polygon interior angles. Well, hopefully by this point, everybody knows that a triangle sums to 180 degrees of the interior angles. And the interior angles would be that, and that as shown. Okay, good. And then probably everybody knows a quadrilateral, or they probably think of it more specifically as a rectangle, square, parallelogram, sums to 360 degrees in total. If that were a rectangle, it's 90, 90, 90, 90, a 360 degree sum. What about a different shape, a pentagon, an octagon? So this begs the question here, what is a polygon? Let's digress for a second to talk about a polygon. A polygon is essentially a shape that's closed. It's made up of straight lines, and it's in 2 dimensionals. So any closed shape made up of straight lines is a polygon. A circle, not a polygon, no straight lines. This shape, not a polygon, it's not closed. Okay? So what are our polygons? Well, we have a triangle with n equals 3 sides. I can't have n equals 2 sides in Euclidean geometry, that is planar geometry, because I can't close a shape with 2 sides. I have a quadrilateral with n equals 4 sides. If n equals 5, we call it a pentagon. N equals 6, we would call that a hexagon. And now we're really stressing my ability to draw these. Next would be a heptagon or a septagon for n equals 7, an octagon for n equals 8, a nonagon for n equals 9, a decagon for n equals 10. Good lordy, I don't think I even know what 11 is. And a dodecagon for 12. My favorite polygon is a chiliagon. It's spicy with 1,000 sides. But you also have megagons, googleagons, so on and so forth. So it pays to know your basic polygons, what they're called, how many sides they have. And we have a concept of whether they're convex or concave. Convex simply means they open outward. That means that every vertex, which is the point where two sides meet, the point is outward, not, say, inward. For example, that point there would be inward. That would be a concave polygon. So we deal generally with convex polygons. Our rules work for concave as well. They get a little funky, but you're not likely to see them. The other case is a simple versus a complex polygon. A simple polygon is basically everything you're going to see, everything you see on the board here. A complex polygon is where the lines actually cross. So this star, for example, is a closed shape in 2 dimensionals, made up of straight lines. It's a polygon, but it's a complex polygon because all the lines intersect. And when that occurs, all our rules for sum of angles, etc., they fall apart. Don't even try to attempt them. And you will not see that on a problem. Okay. Last but not least, we have a concept of regular versus irregular polygons. Regular means all the sides and all the interior angles are exactly the same. Think of a square. That is a regular quadrilateral. Think of an equilateral triangle. That is a triangle with all the same sides and all the same interior angles. Okay? With that said, we want to know what's the sum in general of the interior angles in degrees of various polygons. Well, there is one general rule, and it's the sum of interior angles in degrees is 180 times n minus 2, a fact that's worth knowing for the exam. Okay? So for a triangle, that's 3 minus 2 times 180. Aha, 180, that works. Quadrilateral, 4 minus 2 is 180, 360, that works. And now I can figure out from this formula a 5-sided polygon, a pentagon. What's the sum of interior angles? Well, it's 5 minus 2, 3 times 180, or 540. For a hexagon, it would be 6 minus 2, or 4 times 180, 720, and so on and so forth. I can calculate the sum of interior angles. I can also use this to calculate average interior angles, which, by the way, is the interior angle of every vertex or every angle on a regular polygon. And that would just be the sum divided by the count. So if I had 720 total interior angles on, say, a hexagon with 6 sides, I would divide that by 6, and I'd realize I'd have 120 degrees interior angle. That would be the average interior angle of every hexagon, or for a regular hexagon, exactly the interior angle at every vertex. A related idea is that the sum of exterior angles for any polygon is 360 degrees. Notice that, 360 degrees. Not a function of the number of sides, just a fixed constant amount, regardless of how many sides my polygon has. This also means the interior plus the exterior angles at any given vertex must sum to 180 degrees. We looked at our theorem before. The sum was 180 times n minus 2. Where do we think that minus 2 times 180 came? It was the 360. We're subtracting the exterior angles. So at every vertex, interior plus exterior equals 180. You're not really going to use that on the exam because that requires knowing the definition of exterior angles, which can be a little particular. But that said, let's look at a quick example. If I had a triangle and I had x degrees were my exterior angles, let's suppose that equaled, I don't know. I want to figure out what it equals, given that I have the opposite interior angles of 75 degrees and 40 degrees. Well, guess what? I know that angle is an angle along a line. So it's going to be whatever x is, this is going to be 180 minus x, because x plus this missing angle must sum to 180 for angles along a line. Now, I also know the sum of interior angles of my triangle are 180, so 75 plus 40 is 115, plus the 180 minus x must be 180 itself, which means x is, guess what, 115 degrees. This is called our exterior angle theorem. It says the exterior angle of a triangle is equal to the sum of the two opposite interior angles. All we need to know was our angle theorems 1, 2, and 3 to figure this out. Okay, next important concept, and this has a lot of implications. Transversals of parallel lines. In fact, every time I see the word parallel lines, I immediately think transversals, which immediately sets up similar triangles and then proportion equations. Almost every time on a problem. Let's look at the transversals of parallel lines and what that theorem says. So if I have two horribly drawn parallel lines, call them M and N is parallel to N, my transversing line, call that P, is the transversal of my parallel lines. I know alternate interior angles are congruent. They're the same measure again. So we call those alternate interior, which is a fancy way of saying they're inside the parallel lines and on opposite sides of the transversal. Okay? They're kind of opposite corners if we think about it. Number 2. Well, I'm going to apply my vertical angle theorem and show that that's x, because that's a vertical angle to that x. Which means what? That means these two angles are also congruent. Well, we call those angles corresponding angles. So it's also true that corresponding angles are congruent of the same measure. Okay, I've got another vertical angle there, so that must be x. Well, now I can say these angles are therefore congruent. Well, what do we call those? Those are alternate exterior angles, alternate sides of the transversal, but exterior to the parallel lines. All of these angles are congruent, and they all can be derived from the first one, that alternate interior angles are congruent. In most cases, we're going to see alternate interior angles or corresponding angles in problems to work with. We should also note one thing. Y is the angle along a line with x. It is true if I have parallel lines, the two adjacent interior angles must sum to 180 in degrees. That is also true, so I might write that as number 4. Actually, I'm not going to write it because I wrote it out right there already. So let's see this theorem in action in a couple different examples. Suppose I had the triangle as shown. We'll call it A, B, C. And I had line DE that's parallel to AC. Well, what do we know? If this is parallel, effectively, I've got two parallel lines. If I extend them beyond the triangle, and I've got a transversing line that cuts through them. That means the corresponding angles must be congruent. Those two angles are the same. Likewise, these angles are part of a transversal or corresponding angles in a transversal. They too are congruent. And anytime I have two angles that are the same in a triangle, I know they're similar triangles. So I can say this triangle and the big triangle are similar, which has various implications. In particular, it leads to the following theorem. If I call this A and this segment B, this segment C, and this segment D, I will know A over B, the quotient of the two segments, equals the other quotient of the two segments, C over D. I basically have a proportion equation. We call this our side splitter theorem. And that's a direct consequence of our transversals of parallel lines. Also, if I have a triangle where one angle is being bisected right there and there into two congruent angles, I know the following. If that's A, that's B, that's C and D, again, the same proportion equation holds. A over B equals C over D. That's also a consequence of our transversals of parallel lines. We call that our angle bisector theorem. So not only are transversals of parallel lines very useful for identifying similar triangles, but they have particular theorems and related consequences as well. We can see another consequence of our transversals of parallel line theorems in parallelograms. So suppose we have parallelogram ABCD, where BC and AD are parallel, AB and CD are parallel, and we've got interior angles X and Y. What do I know here? Well, based on my transversals of parallel lines, I can figure out that my adjacent interior angles in a parallelogram must sum to 180. So x plus y equals 180 degrees in a parallelogram. That's one consequence. Also, if I figured it out, I've got two sets of transversals of parallel lines, if I want to think about it that way and that way. And without getting into too much detail, if you think about it, you'll realize this angle must be x and this angle must be y. Interior angles across the parallelogram are the same. So I have x equals x on opposite interior angles. Likewise, opposite interior angles at B and D are the same. So opposite interior angles of parallelograms are congruent. Quite a few implications from our simple transversals of parallel lines. Our next angle theorem indicates there's a relationship between the interior angles of a triangle, or any polygon for that matter, and the opposite side lengths. So let's think of triangles. The largest side of a triangle is opposite the largest interior angle. And we can see that in, say, for example, a right triangle. The largest interior angle in a right triangle is our 90-degree angle. That is opposite the longest side of our triangle, our hypotenuse. Likewise, the smallest interior angle is opposite the shortest side. So for example, if this were 30 degrees and this were 60 degrees, the shortest side of this triangle would be opposite the 30-degree angle. It would be right here. Lastly, equal interior angles are opposite equal side lengths. Well, where do we see this? How about an isosceles triangle? And everybody should get to know the various names of triangles: by angles, by lengths, acute, right, obtuse triangles, isosceles, equilateral, scalene triangles. You should be well aware of what those are. So isosceles has two congruent sides, but opposite those two congruent sides, you should know the interior angles opposite the sides are congruent. They're the same measurement. So what are we effectively doing? We're basically ordering from low to high side lengths based on the interior angles. Now, is this a direct relationship? Do we know the nature of that relationship? Can we quantify it? No, we cannot. That's where trigonometry comes in. Trigonometry quantifies the relationship between the interior angle and the opposite sides. In geometry, we just know how to order them based on this theorem. So what's a problem that might come into play in this? How would we utilize this? What if I had the following two triangles? We'll label them A, B, C, D. What is the longest side? Well, a lot of students will look at it and say, okay, I got 30 degrees, 50 degrees, 60 degrees, 70 degrees, 90 degrees. 90 degrees is my largest interior angle. Therefore, opposite that is my longest side. This BD must be my longest side. Wrong. Why? Because this applies for any given triangle, and that's an important point in executing it. It does not apply across triangles. While BD is the longest side of triangle BCD, because it's opposite the largest interior angle of that triangle, that's true. But it's opposite 50 degrees, which is actually filling in the missing angle in ABD. That would be 60 degrees to get a 180-degree sum. I can see 50 degrees, angle A, is the shortest or smallest interior angle of triangle ABD, which means BD is the shortest side of triangle ABD. It is not the longest side of the figure. The longest side for triangle ABD is opposite the largest interior angle, 70. Therefore, AB is the longest side of triangle ABD, which has a longer sides than triangle BCD. This is the longest side of the figure. So again, when we're using this theorem, remember it applies to a given triangle, not across triangles. The next set of angle theorems pertain to circles. So suppose I had a circle with center C as shown, and I had the following rays that extend from the vertex where the center there is the vertex of this angle. And suppose that angle is 80 degrees. We would call that my central angle because the vertex is at the center of the circle. So that is my central angle. And suppose I had another angle in orange that was x degrees, and we would call this one with a vertex on the surface of the circle an inscribed angle. And there are multiple inscribed angles anywhere I put that vertex on the circumference of the circle. The central angle theorem says if my inscribed angle and my central angle span the very same arc, which is along their circumference, that would be known as arc AB. If they span the same arc, then it must be true that my inscribed angle equals 1/2 my central angle. So what would x be in this case? If my central angle is 80 degrees, 1/2 of 80 degrees means my inscribed angle x must be 40 degrees. And sure enough, there x is 40 degrees. That's my central angle theorem. The inscribed angle is 1/2 the central angle if they span the same arc. Well, so wait a second. Let's play around with that a little. What if I had that angle? That also spans arc AB, which means that angle might look very different than x, but it's also 40 degrees. Okay, well, let's keep going a little bit. What if I had that angle? That again looks very different, but it spans arc AB, so that too must be 40 degrees. So notice any inscribed angle that spans the same arc, those must be congruent as well. Let's see an example of the inscribed angle theorem at work. I have 32-degree angle shown there, and I know that spans the arc from here to here. I also notice I have another inscribed angle on the surface of the circle that spans the same arc. So I know that must also be 32 degrees. And I see I then have two angles in the triangle with my unknown angle. So that means the unknown angle plus 85 plus 32 must equal the sum of interior angles in a triangle, 180. That means the missing angle is 180 minus 85 minus 32, or 63 degrees. My missing angle here is 63 degrees. Okay, let's suppose I have another question, and I want to know, let's label this A, B, C, and D. Let's suppose I wanted to know if A, B is parallel to CD. It's not obvious from the diagram. It could be, but not very clearly. So how would I go about looking at that? Well, what other angle theorems do I know? I know that's a vertical angle, so that must be 85. And if that's 85, then I have 32, 85. This must be 63 degrees. Again, my interior triangle sum must be 180 degrees. So what do I have here? I have two similar triangles. Why are they similar? Because they have the same interior angles. We'll learn about that in our similar triangle section. But are these parallel? Well, let's think about that. AB would be there. CD would be there. If they are parallel, that means the alternate interior angles in the opposite corners there must be the same. They're not the same. One's 63, one's 32. I have similar triangles, but there's no reason, and it's not true, that AB is parallel to CD. There are a few corollaries to the central angle theorem worth noting. The first one is that a radius from the center of the circle to a tangent line, which intersects the circle at exactly one point, must be perpendicular to that tangent line. So two right angles would be formed upon that intersection. So if I had, for example, say a triangle, let's connect that line, and I knew this was, say, 3, and this was length 5, what would my missing length be? Well, right away I know my radius would have to be 4. This is a 3, 4, 5 Pythagorean triple, one of our special cases for right triangles that you definitely want to know for the exam. Another corollary to the central angle theorem is that any angle or triangle inscribed in a semicircle must be a right triangle or a right angle. So why is that? Well, if we think of the diameter as our central angle spanning AB, that spans 180 degrees. Well, guess what? Our inscribed triangle also spans arc AB, the very same arc. So the central angle theorem comes into play because this is an inscribed angle with a vertex on the circle. As a result, my inscribed angle equals 1/2 the central angle. And since our central angle in this case is 180 degrees, the inscribed angle must be 90 degrees or a right angle. So that has a few implications we might want to take note of. Any triangle, if I drew that triangle, that's a right triangle. If I drew that triangle, that's a right triangle. It doesn't matter. If it's inscribed in a semicircle, it's a right triangle. So let's suppose I had the following problem. I knew this chord, call this CB, had a length of 6, and I knew the chord AC had a length of 8. What is the radius of my circle? Well, I know this is a right triangle with sides 6, 8, and therefore the hypotenuse must be 10. Again, that's a 3, 4, 5 Pythagorean triplet. It's just scaled 2 times. Well, okay, be careful. The radius isn't 10. The radius is half of 10. That's the radius. My radius would be 5 units long. Additionally, if I had a quadrilateral inscribed in a circle, where all 4 vertices lie on the edge of the circle, we would call that a cyclic quadrilateral. And as a corollary to the central angle theorem, if that angle is x and that angle is y, I know x plus y must equal a sum of 180 degrees. Well, how do I know that exactly? Well, if I think about it, that's A and B, if we want to label it. X spans minor arc AB. Y spans major arc AB. Major arc is greater than 180 degrees. Minor arc is lesser. Combined, that's 360 degrees of arcs spanned. Notice each is an inscribed angle. Therefore, they must sum to half 360 or 180. And that's the reason why this is true. So let's try an example. If I knew angle A were, say, 95 degrees, that means the angle opposite in the cyclic quadrilateral, angle B, must sum to 180 degrees with the 95 degree angle. So angle B must be 85 degrees. Let's continue our discussion of central angles to include the lengths of arcs, which is essentially that green pizza crust length on the outside of my central angle there, and sectors, which is the pizza slice itself, and we would calculate generally the area of that sector. So I like to think of it as pizzas. We've got pizza slices and pizza crusts. Kind of an easy analogy for sectors and arcs. So suppose my circle had a radius equal to 3 units long. What would the length of that green arc be? Well, notice it looks kind of analogous to my angle measure in pink. And it's that logic we're going to use. I'm not going to bore you with formulas. I'm just going to extend ideas so you learn the concept. I can say the ratio of my central angle, 80 degrees there, to a full rotation around the circle, 360 degrees, is essentially the same as the ratio of the length of my arc for that sector, the green shown, compared to the entire circumference of the circle. Note the green to blue is essentially the same ratio as my 80 degree angle measure to a full 360 rotation around a circle. And that's the equation we're going to set up to solve for missing arc lengths. The central angle to 360 degrees, a full rotation, is the same as the arc length in green to a full circumference, the full distance around the circle. Well, we have some of that information that we can go ahead and compute that in this case. Let's give this a try. My central angle is 80 degrees, as shown. Dividing by a full circle rotation in degrees to keep my units the same of 360 is the fraction of the circle my central angle composes. So my arc should be the same fraction of the full circumference. So let's call my arc length A, and we'll divide that by the circumference of the circle of radius 3. That's going to be 2 pi times my radius, which is 3. And now I can solve for A. I'm going to multiply by 6 pi on both sides. A equals 6 times 80 times pi divided by 360. And now I can simplify and cancel. A equals 4/3 pi. And if we were to approximate that, we know pi is a little more than 3. So this number is just going to be a little bit more than 4 units long. But make sure to keep it expressed as pi because most answer choices on the exam will express in pi. 4/3 pi would be the answer. The sector of the circle carved out by the central angle is the green area shown. It's essentially the pizza slice. The fraction of the central angle to the full rotation around a circle is the same fraction of the pizza slice, the sector carved out of the entire circle. So that same proportion is going to hold. So if I have a central angle of 80 degrees again, I can say the following. The area of my sector divided by the area of the circle is the same as the central angle divided by a full rotation around the circle, which is 360 degrees. So what would that look like in this case, assuming, again, my radius of my circle equaled 3 units long? Well, the area of my sector, let's call that A. We're trying to solve for that green area, divided by the area of my circle. Well, if it's radius 3, the area of a circle is pi r squared. So that's pi times 3 squared. And that, in turn, equals the ratio of my central angle to a full circle rotation, 80, in this case, to 360. The area of my sector is 2 pi. Conceptually, that ratio of the central angle to a full rotation is the same ratio as both the area of the sector to the full circle area and the length of the arc to the full circumference around the outside of the circle. Up until this point, we've only measured angles in terms of degrees, but sometimes angle measures will be presented as a function of pi, which is a clear indicator that they mean radians. So what are radians? Well, if we remember degrees essentially have 360 degrees for one full rotation around the circle. Well, what exactly is a radian then? Well, radian is, imagine you took this radius and it was a string and you laid it around the circle. We know from the circumference of the circle it would go around 2 pi times, or just over 6 times, about 6.28. So if I took that radius, I'd get about 6.28, or 2 pi strings to get around the circle. The radian is the angle formed by 1 radian around the circumference. So if that's the first radian, or first radius around the circumference, that would form an angle to my central angle that would look like that. In degrees, that's going to be about 60 degrees. It's 360 divided by 6. A little less than that, 59.7 degrees or so. And that is what we would call 1 radian. So what is the conversion between radians and degrees? Well, if you think about it, if I go 2 pi is around a full circle, pi is half a circle in radians, and that will equal half a circle in degrees, 180. You can use whichever conversion you want. 2 pi equals 360. Pi equals 180 seems to be the one students prefer. With this, I can adjust my angle measures from radians to degrees. For example, what would pi over 6 radians be equivalent to in degrees? Well, that would be 180 instead of pi divided by 6 equals 30 degrees. Pi over 6 equals 30 degrees. Pi over 2 would therefore equal 90 degrees. What would 3/4 pi represent? 3/4 pi would represent 3/4 of 180 or 135 degrees. Starting to get the hang of it? What if I had 3 pi over 2 as an angle measure in radians? That would be equivalent to 180 times 3 halves or 1.5. That would be 270 degrees. So let's try our example again. Radius equals 3. And in this case, I'll have a central angle. Let's call that pi over 3. What is the measure of the arc that spans that central angle? Okay, well, I know the ratio of the arc length to the full circumference of the circle from our last lesson equals the ratio of the central angle, which is now in radians. That's pi divided by 3 to the full rotation of the circle. Well, I'm not talking 360 degrees anymore. A full rotation of the circle is going to be 2 pi. So I'm going to set up that same proportion. Conceptually, this is exactly the same. I'm just using radians instead of degrees. So I know the circumference of my circle is going to be 2 pi r. That's 2 pi times 3. I'm solving for my arc length. Let's call that a. And that equals pi over 3 over 2 pi. Well, guess what? The pi's cancel. 1/3 divided by 2 is 1/6. Then I'll multiply by 6 pi on both sides. I will get an arc length equal to pi. In geometry, we learned that the sides opposite interior angles of a triangle are related to the interior angles. Larger angle, larger opposite side. Smaller angle, shorter opposite side. The study of trigonometry helps us quantify that relationship. It begins with some definitions around trigonometry ratios and right triangles. And generally, we're going to start with our basic primary trig ratios, sine, cosine, tan x, and our secondary trig ratios, cosecant, secant, and cotangent of x. We'll define them right here. You might remember them as SOHCAHTOA as an acronym. You need to know them however you remember it. The sine of x, as shown here, is the opposite side in red over the hypotenuse, the longest side of the right triangle. The cosine is the adjacent side in green over the hypotenuse, and the tangent of x is the opposite over the adjacent. Know these primary trig ratios by memory. The secondary trig ratios, the easiest way to remember them is that they are the reciprocal of the primary trig ratios. The cosecant of x is 1 over sine. The secant is 1 over cosine. The tangent of x is 1 over cotan x. Be careful. Don't mix up the fact that the sine corresponds to the cosecant and the cosine corresponds to the secant. The ones that sound alike are not the ones that connect between primary and secondary trig ratios. You should be able to take given side lengths of any triangle and calculate all the primary and even the secondary ratios as shown. I might also add a couple points here that the tangent can also be expressed as the sine of x divided by the cosine of x. Likewise, the cotangent, the reciprocal, would be the cosine of x divided by the sine of x. On occasion, that can be a useful ratio to know. You definitely want to know all your special right triangles for the exam. As we had the Pythagorean triples, the 3, 4, 5, 5, 12, 13, 8, 15, 17, or any scaled version of those. They could be doubled, 6, 8, 10, or halved, whatever it was. Those were very important to quickly get the answer. Even more importantly are the special right triangles from trigonometry. You need to know these. You need to memorize these. I can't tell you how many times I tell students to do that. They don't do it, and for whatever reason, well, like teenagers, they don't want to do it, and eventually we get it into them. They learn, I have to know these. The first one is the 30, 60, 90 right triangle. If my hypotenuse is 2x, the side opposite the 30-degree angle is x. It's 1/2 that. By the way, that means our sine of 30 degrees equals x over 2x, or 1/2. You should know that by heart. Sine of 30 is 1/2. The side opposite the 60-degree angle is root 3 times that side that's opposite 30. So root 3x. You need to know these ratios. I'm going to put it in terms of a unit hypotenuse. In 30, 60, 90, if I have 1 for my side length of my hypotenuse, it's going to be 1/2 for the side length opposite 30, and root 3 over 2 for the side length opposite the 60. Note that's the same ratios as shown in the diagram. The second one we want to know is the 45, 45, 90 right triangle. It's an isosceles right triangle. The sides opposite the 45 degrees must be congruent. Therefore, our side lengths are, if I call this x and this leg x, the diagonal will be root 2x. By the way, I know the diagonal of a square is root 2 times the side length, so that's kind of the same thing going on here. And if I thought of it in a unit as a unit hypotenuse, so opposite the 90, the side length are 1, then my sides, 45 degrees and 45 degree opposites, would be root 2 over 2, root 2 over 2. These are the ratios. Again, that's the same ratio as shown in the diagram. Either way you want to think about it, I know it's taught kind of a couple different ways. One of these is probably the one you've seen. You need to learn and memorize these special right triangles. Why? Because it's really important. You can actually calculate or estimate all your trig values just from the series of angles from 0 to 30 to 45 to 60 to 90, and then essentially they just repeat at different terminal angles. It's a question of whether they'll be positive or negative given sine or cosine. The cofunction rule is another topic that comes up frequently on the exam related to trig. This says the sine of x equals the cosine of its complementary angle, 90 degrees minus x. So if we think about it, the sine of x is the opposite over the hypotenuse. In any right triangle, the other angle must be 90 minus x, the complement to x. The cosine of that angle is the very same ratio of sides, the adjacent to the hypotenuse, but the adjacent to 90 minus x is the opposite of x. So they're literally the same ratios. Therefore, the sine of x equals the cosine of 90 minus x in all cases. This is called our cofunction rule. By the way, it's also true the cosine of x equals the sine of 90 minus x. And even tan, cotan are cofunctions. Let's look at a couple examples of the cofunction rule in action. Sine of 53 degrees minus the cosine of 37 degrees. Don't panic, because these are ugly numbers. The cosine of 37 degrees is really just the cosine of 90 minus 53 degrees. This is 90 minus x if the sine of 53 is x, which means I'm subtracting the number from itself. The answer must be 0. What if the cosine of x is 0.36? What is the cosecant of 90 minus x? The cosecant is our secondary trig ratio. That's 1 over the sine, and the angle would be the same, 90 minus x. Well, we know the sine of 90 minus x equals the cosine of x. So this essentially would be 1 over the cos x, which is 1 over 0.36. That would be your answer. Whatever that evaluates to, that's the cosecant of 90 minus x. Okay, what if I had cosine 2x plus 20 equals sine 5x minus 10? What is x? Slightly different presentation. But again, I'm going to use my cofunction rule as a way to set up the algebra. In order for the cosine of an angle to equal the sine of another angle, those angles must be complementary given our cofunction rule. It's another way of looking at it. So the angle that represents 2x plus 20 plus the angle that represents 5x minus 10, which must be a complementary angle, sums to 90 degrees. Now I can begin to do my algebra. 7x equals 90 plus 10 is 100, minus 20 is 80. X equals 80 divided by 7. It is also useful to recognize the graphs of the trig ratios and understand how they're formed. So for example, we have what appear to be two sine waves, no pun intended, because one in blue is the sine of x. The orange curve is the cosine of x. Notice how they range between -1 and 1. Well, if you think about it, the sine and the cosine are always divided by the hypotenuse, the longest side of the triangle. So the absolute value of either ratio must always be less than 1. How do we actually determine those curves? Well, one way we do it is we start with a unit circle and we rotate our radius, which is the hypotenuse of a right triangle, through that unit circle from the first, second to the third and fourth quadrants, and we evaluate what the sine, the cosine, and even perhaps the tangent and other trig ratios are at those angles. So let's take a quick look at how that would work for, say, a 30-degree angle. If I had a 30-degree angle as shown in the first quadrant, the sine of 30 degrees is 1/2 over 1. My vertical line in red there is 1/2. My horizontal leg is √3 over 2. I know that from my 30, 60, 90 triangle. If, however, I wanted to know the sine of 150 degrees, taking me out to the second quadrant, I might notice the terminal angle between 150 and the horizontal x-axis is again 30 degrees. So the sides of the lengths are the same in my triangle. The sine of 150 is effectively the sine of a 30-degree triangle, which is 1/2. And it's still positive. It's in the positive y direction. The horizontal leg is now -√3 over 2. So my cosine of 30 becomes -√3 over 2. Okay, let's keep that exercise going. What if I went into the next quadrant to 210 degrees? Well, 210 degrees, that would again have a terminal angle with the x-axis of 30 degrees. My vertical sine leg is now -1/2. My cosine, my horizontal leg, is still √3 over 2. So the sine of 210 would be -1/2, and the cosine of 210 would be -√3 over 2. And I would continue this exercise until the end. By the way, notice at the points 0 degrees, where we start, there is only a horizontal bar, which means the cosine, the adjacent leg, is the same as the hypotenuse. So that's cosine equals 1. The vertical leg is 0 at 0 degrees, so the sine equals 0. And likewise, as I shift up to 90 degrees, my vertical becomes the entire hypotenuse or radius. So the sine of 90 degrees is 1, but the horizontal leg is 0, so the cosine of 90 degrees is 0. And you can see how that matches our graphs. So this might sound a little complicated, but like most things, it's best learned by trying some examples. Let's take a look. The sine of 30 degrees would equal the A divided by 2A in the diagram below. That's 1 divided by 2. Everybody should get to know that. Tangent of 45, that would be the x on the opposite side of 45 divided by the x adjacent to 45, which is x over x, or simply 1. Cosine of 60 degrees. We know our cofunction rule. The cosine of 60 is the sine of 90 minus 60, so it must equal the sine of 30. 1/2 is the cosine of 60. Cosine of 180. So if we remember our unit circle, when we go all the way across that unit circle from 0 degrees to 180 degrees, we go from positive x values to negative x values. The cosine is the horizontal or adjacent, so cosine of 180, if we recall, is -1. The cosine of 270 equals, same idea, 270 would be 3/4 of the way around the circle. It would be strictly a vertical. There would be no horizontal leg at 270. Therefore, the cosine of 270, like the cosine of 90, is 0. The cosine of 0, we should know, is 1. The sine of 90 is 1. The sine of 0 is going to be 0. The sine of pi, don't forget, pi radians equals 180 degrees. So this is effectively the sine of 180 degrees, which is 0. Again, at that point, you're all horizontal to the left. There is no vertical or any sign in our unit circle. Let's try a few harder examples you might see on the exam in radians and angles that are greater than 90 degrees. Sine 4 pi over 3. So essentially this is 1 1/3 pi if we think about it. Pi radians, remember, takes us from 0 all the way around to pi. And then another pi over 3 is essentially 180 over 3, another 60 degrees. So that would take us out to right about here. The equivalent, this would be 4/3 pi. And that would be the equivalent of 60 degrees in my third quadrant. So my sine would be negative. My vertical goes downward, and it would be 60 degrees. That's a sine of √3 over 2. So the answer here should be negative √3 over 2. How about the sine of 3 pi? Well, I go pi. I would go pi again back to 0, and I'd go pi again. So this is effectively the sine of pi, which we know is the sine of 180 degrees. There's no vertical component to my unit triangle, so the sine is 0 divided by the hypotenuse. The sine of 3 pi is the sine of pi, it's the sine of 180 is 0. Okay, that was a mouthful. Tangent, pi over 4. Okay, pi over 4 is essentially, given our conversion, pi radians for 180 degrees is 180 over 4 or 45 degrees. This is essentially the tan of 45 degrees, which means my leg lengths are going to be the same. The answer is 1. Sine of 7 pi over 6. So 7 pi over 6, again, takes us just beyond pi. In this case, we go 1/6 beyond pi. That's pi over 6 or 180 over 6, 30 degrees. So in this case, it looks like our terminal angle, poorly drawn, I apologize, there is going to be 30 degrees in the third quadrant. That would be 7 pi over 6. So 30 degrees, the sine of 30 degrees is 1/2, and it is negative. It's below the x-axis, so it's negative 1/2. That would be the answer. How about the cosine of negative pi? Well, if I went negative pi, I'd be going in the reverse direction around my circle to pi, which doesn't really make a difference if I went clockwise or counterclockwise. I am still essentially cosine of 180 degrees, which is -1. Remember, our cosine is the horizontal component in our unit right triangle, and that horizontal component here is -1. Cosine of 5 pi over 3. So in this case, we're going to go pi, essentially, if you want to think about it, plus 2/3 pi. So we'll go around 1 pi, and then we'll go around 2/3 pi, which is essentially 2/3 times 180, or another 120 degrees, which puts us right about there. 5 pi over 3. I would get 300 degrees. That means our terminal angle is 60 degrees in the fourth quadrant. So the cosine here is the horizontal leg. It will be positive. The cosine of 60 degrees, we know, is 1/2. So it's going to be plus 1/2 for the cosine. And that's how we go about answering these types of problems.